In this video, we're going to talk about composite functions, how to find them, how to determine the domain of the composite function, and how to use them to test if two functions are inverses of each other. So let's begin. Let's say if f of x is equal to 1 over x, and g of x is equal to x plus 3. How can we find the composite function f of g of x? A composite function occurs when you have one function inside of another. So notice that f is written first on the left. So f is the outside part and g is the inside part. So you can rewrite it as f of g of x. So g of x, the inside function, is the input of the function. F is the output. So to find this function, we need to take g and insert it into f. So f of x is 1 divided by x. Now, instead of writing x, we're going to replace the x with g. And in this case, g is x plus 3. So instead of writing x, we're going to write x plus 3. So that's how you could find the composite function. Now that we have the composite function, what is the domain of the composite function? What you need to realize when looking for the domain of the composite function is that the domain is restricted by the domain of the input function, not the output function. So in this particular example, we said that g is the input function and f is the output function. Now for g of x, it's simply x plus 3. We don't have any fractions, we don't have any radicals, no logarithms. So if you have a polynomial without any fractions, the domain will be all real numbers. So the domain for g of x is from negative infinity to infinity. There's no restrictions on the input g function. Now what about the output function? What restrictions are there for the domain of f of x? Whenever you have a fraction, you can never have a 0 in the denominator of a fraction, otherwise it will be undefined at that point. So x cannot equal 0 for f of x. Now for the composite function, the domain is dependent on the input function. Since we don't have any restrictions on the input function, we don't have to worry about it. Even though there's a restriction on the output function, that's not going to affect the composite function. The input function affects the composite function, not the output. So all we need to do for this example is we need to find out what value of x will make the denominator equivalent to 0. So we know that x plus 3 cannot be 0. That's a restriction for the composite function because we have a fraction. So therefore x cannot be negative 3. It can be any other number except negative 3. Now how do we represent this answer using interval notation? The best way to do it is to graph the solution on a number line. So x could be anything except negative 3. Since it can't be negative 3, we need to use an open circle at negative 3. It can be anything greater than negative 3 or anything less than negative 3. All the way to the left we have negative infinity, and to the right we have positive infinity. So to represent the solution for the left side, it's going to be negative infinity to negative 3, which we can write it like this. Now negative 3 is not included, so we need to use a parentheses instead of a bracket. And then union, for the right side, it's negative 3 to infinity, except negative 3. And so that's how you can write the answer using interval notation. So that is the domain for the composite function f of g of x. Now, what about the reverse? What about g of f of x? Feel free to pause the video, find the composite function g of f of x, and also determine what the domain is and represent the solution using interval notation. So first, let's find g of f of x. So this is the same as this expression. You can write it this way. So f is inside of g. So we're going to take 1 over x and replace it with x. So g is x plus 3. But instead of writing x, we're going to replace it with 1 over x. So this time, f of x is the input function, and g of x is the output function. Now, the input function has a restriction. As we said before, x cannot equal 0 for f of x. So that restriction will exist for the composite function as well. The composite function, which is 1 over x plus 3, we still have a fraction, and in this fraction, x cannot be 0. So this is the domain for the composite function. And to write it using interval notation, it's negative infinity to 0 union 0 to infinity. It's everything except 0. Let's try another example. Let's say f of x is equal to the square root of x minus 2, and g of x is equal to 1 over x plus 3. Find the composite function f of g of x and determine the domain for the composite function. So g is inside of f. So f is going to be the square root of x minus 2. But let's replace x with 1 over x plus 3. So it's 1 over x plus 3 minus 2. So g is the input function. So we need to find the domain of the input function. We don't have to worry about the domain of the output function. So we don't have to worry about this for now. So here we have a rational function. We have a fraction. And we know that the denominator cannot be 0. So therefore, x cannot be negative 3. So that's the first restriction. Now, whenever you have a radical, the inside of a square root cannot be negative if the index number is even. If it's odd, it could be negative or positive. Doesn't matter. So 1 over x plus 3 minus 2 has to be equal to or greater than 0 if the radical is in the numerator, which it is. You can see it as being over 1. If you have a radical in the bottom of a fraction, then it's not greater than or equal to, it's just greater than 0. Now, to solve for x, let's add 2 to both sides. So 1 over x plus 3 is greater than or equal to 2. And now let's multiply both sides by x plus 3. So we're going to have to make some space here. Let's move that up. So we now have these two will cancel, and on the left it's just going to be 1. On the right side it's going to be greater than or equal to 2 times x plus 3. If we distribute the 2, it's going to be 2x plus 6, and if we subtract 6 from both sides, 1 minus 6 is negative 5. And then we need to divide by 2. So based on this, it appears as if x is less than or equal to negative 5 over 2. Now we got to be careful with this answer, because it may not always be correct. Whenever you have two critical numbers, in this case negative 3 and negative 5 over 2, it is wise to check your answer using a number line. Nevertheless, this number is important because it's a turning point in this function. So let's test the answers using a number line. Negative 5 over 2 is the same as negative 2.5. So we have negative 3 and negative 2.5. These are the main points of interest. So if we plug in a number to the right of negative 2.5, let's say 0, this equation, is it true or is it false? So 1 over 0 plus 3, which is 1/3, minus 2, is that greater than or equal to 0? 1/3 is about 0.33. 0.33 minus 2 is negative 1.67, which is not greater than 0. That's less than 0. So it's not true on the right side. Now what about a number to the left of negative 3? Let's try negative 4. So negative 4 plus 3 is negative 1. And 1 divided by negative 1 is negative 1. And negative 1 minus 2 is negative 3. Negative 3 is not greater than 0. And it's not equal to 0 either. So the left side does not work. It's not true for the left side. So let's put an X. Now what about a number between negative 3 and negative 2.5? Let's try negative 2.9. So 1 divided by negative 2.9 plus 3 minus 2, is that greater than or equal to 0? Negative 2.9 plus 3 is the same as 3 minus 2.9, which is 0.1. 1 divided by 0.1 is 10. 10 minus 2 is 8. 8 is greater than 0, so that is true. It works in that region. So let's put a check. Now the next thing that we need to take into account, at negative 3, do we have an open circle or a closed circle? Notice that it does not include negative 3, so it's an open circle at negative 3. Now what about a negative 2.5? Does it include it? If we plug in negative 2.5 into x, negative 2.5 plus 3, or 3 minus 2.5, is positive 0.5. 1 divided by 0.5 is 2. 2 minus 2 is 0. 0 equals 0, so negative 2.5 is included as a solution. So therefore, we have a closed circle at negative 2.5. So this is the answer using a number line. So we can clearly see the solution in interval notation. It's going to be from negative 3 to negative 2.5. But since it includes negative 2.5, we're going to use a bracket. So this is the domain of the composite function for f of g of x. Let's try a completely different example. So let's say if f of x is equal to the square root of x minus 5, and g of x is 1 over 8 minus x. Find the composite function g of f of x, and go ahead and determine the domain of the function. So the input function is f of x. What is the restriction on this function? So for square root functions, the inside has to be equal to or greater than 0. So if you add 5, x has to be greater than or equal to 5. So that's the restriction on f. Now let's go ahead and find the composite function. So let's put f into g. So g is 1 divided by 8 minus x, but instead of writing x, we're going to put the function for f, so which is square root x minus 5. So now we know that we have a fraction, and the bottom of the fraction cannot equal 0. So 8 minus the square root of x minus 5 cannot equal 0. Now let's add the radical to both sides. So if we add square root x minus 5 to both sides, we can see that 8 cannot equal root x minus 5. To get rid of the radical, let's square both sides. So 64 cannot equal x minus 5. If we add 5 to both sides, 64 plus 5 is 69. So x cannot equal 69. If you plug it in, 69 minus 5 is 64. Square root of 64 is 8. 8 minus 8 is 0. We can't have a 0 in the bottom. So now, how can we combine these two restrictions? We see that x can't be 69, and x has to be greater than or equal to 5. So before we write the answer using interval notation, let's plot the solution on a number line. It helps if you do it that way. So let's say 5 is to the left and 69 is somewhere to the right. Now, we know that x cannot equal 69, so we have an open circle. But x can equal 5, and it's also greater than 5. So if it's everything to the right of 5 except 69. It could be anything greater than 5. Now, how can we represent this solution using interval notation? Now, there's two parts. This is the first region that is shaded because there's a disconnect at 69. And this is the second region that is shaded. All the way to the right, we have positive infinity. So for this region, the answer is 5 to 69. 5 is included, so we're going to use the brackets because we have a closed circle at 5. But we need to use parentheses around 69 because it's an open circle. Now for the second part, we can see that it ranges from 69 to infinity. So we're going to write union to connect those two parts, 69 to infinity. And that 69 looks terrible. So this is the answer. Here's the last example on composite functions and their domains. So let's say f of x is 3 over x minus 2, and g of x is 4 over x plus 1. So this time we have two fractions. Find the composite function f of g of x and determine the domain for the function. So g is the input of the composite function, so let's find the restriction on g. For g, x cannot equal negative 1. We can't have a 0 in the bottom. Now, what is the composite function f of g of x? We need to take g and insert it into f. So let's start with f of x, which is 3 divided by blank minus 2. Now let's replace x with g of x, which is 4 over x plus 1. And this is a minus sign. So now, what should we do next? So we know that the denominator of the composite function cannot be equal to 0. So let's write an equation. 4 divided by x plus 1 minus 2 cannot equal 0. So let's add 2 to both sides. So 4 over x plus 1 cannot equal 2. If we cross multiply, 4 times 1 is 4, and then that cannot be 2 times x plus 1, which is 2x plus 2. If we subtract both sides by 2, 2 cannot equal 2x. So x cannot equal positive 1. And you can check your answer by plugging it in. If you plug in 1, 1 plus 1 is 2, and 4 divided by 2 is 2. 2 minus 2 is 0. And we can't have a 0 on the bottom, so x cannot equal 1, nor can it equal -1. So how can we write the answer using interval notation? So let's plot it on a number line first. Here's -1 and 1. So since x cannot equal any of those two values, we have an open circle. But it can be anything else. So it's every other number except -1 and 1. Now notice that there's 3 shaded regions. Here's the first one, here's the second, and here's the third. So therefore, we're going to have 3 parts to our answer in interval notation. So the first part, highlighted in red, is going to be from -infinity to -1. The second part, highlighted in purple, is union -1 to 1. And the third part, highlighted in green, is 1 to infinity. So that's how you can remove -1 and 1 from the domain. So that is the answer for this problem. Now let's move on into inverse functions. Let's talk about how to find them and how to use composite functions to determine if two functions are inverses of each other. So let's say if f of x is 3x plus 5. What would you do to find the inverse of this function? You need to realize that y is the same as f of x. So we can replace f of x with y. That's the first step. The second step is to switch x and y. So x is equal to 3y plus 5. Now you might be wondering, okay, why should we do that? Well, let's say that f of 2 is equal to 3. That means when x is 2, y is 3. For the inverse function, the inverse of 3 is 2. So to find the inverse function, you simply need to switch the x and y values. And that's why we're doing that in the equation. Once you switch x and y, your next step is to solve for y. So let's subtract 5 from both sides. So x minus 5 is equal to 3y. Next, let's divide both sides by 3. So x minus 5 divided by 3 is equal to y. So therefore, we could say that the inverse function, which we can replace it with this y, the inverse function is equal to x minus 5 divided by 3. So that's how you can find the inverse function. Now let's understand the graphical relationship between f of x and the inverse function. If you plot f of x using the slope-intercept form, you can see that the slope is 3, the y-intercept is 5. It's in the form y is equal to mx plus b. M is the slope, which is the number in front of x, that's 3. B is the y-intercept, which is 5. So the graph is going to start at 5, and with a slope of 3, the rise of a run is 3, so you need to go up 3 over 1. So if we draw a rough sketch, the graph should look something like this. Now for the inverse function, this is the same as 1/3 x minus 5 over 3 if you divide x and -5 by 3 separately. So the slope is 1/3 and the y-intercept is -5/3. So -5/3 is about -1.67, which is somewhere over there. The slope is 1 over 3. So the rise is 1, the run is 3. So we need to go up 1 over 3, which will take us to a point somewhere in this region. So now if we graph the 2 points, it looks something like this. And this graph will extend this way. Now, the function and the inverse function, they're reflected about the line y equals x, which is right in the middle. You can see the reflection. So that's how you can tell if two functions are inverses of each other graphically. They have to reflect about the line y equals x. So for example, if you have y is equal to the square root of x and x is equal to root y, these are inverses of each other. The square root of x function looks like this. This is positive root x. Negative root x would look like that, which we don't have. Now x equals positive root y, it looks like this. If it equals negative root y, we would have this region. Notice that these two are inverses of each other. As you can see, there's symmetry about this line, about the line y equals x. Now, going back to the last example, we said that f of x is equal to 3x plus 5, and the inverse is x minus 5 divided by 3. To prove that two functions are inverses of each other, you need to take the composite function. For example, you need to find f of the inverse function of x, and you need to show that it's equal to x. And you have to do it the other way. So you need to take the inverse function of f of x and prove that it's x. If you get the same answer, if both answers are x, then the two functions are inverses of each other. So let's prove that these functions are inverses of each other using that method. Let's start with f inverse f of x. So the inverse function is inside of f. So let's insert this function into x. Now let's simplify the expression. 3 divided by 3 is 1. So we no longer need the parentheses. So it's simply x minus 5 plus 5. Negative 5 plus 5 is 0. So then simplifies to x, which works out. Now let's try it the other way. So the inverse of f of x, let's prove that it's equal to x. So let's take 3x plus 5 and insert it where x is. So it's 3x plus 5 minus 5 divided by 3. 5 minus 5 is 0, so we're left with 3x divided by 3. 3 divided by 3 is 1, so we have 1x, which is x. And so we've proved that these two functions are inverses of each other. Now let's try another example. Let's say if f of x is equal to the cube root of x minus 3, and g of x is equal to x cubed plus 3. Are these two functions inverses of each other? Go ahead and prove it. So first let's find f of g of x. So g is the input function. So let's take this and replace it with x. Or let's replace x with x cubed plus 3. That's what I meant to say. So this is the cube root of x cubed plus 3 minus the 3 that was already on the inside. So 3 minus 3 is 0. So we're left with the cube root of x cubed. The cube root of x cubed is simply x. It's really x raised to the third power divided by 3, which is x to the first power, or simply x. So now let's find g of f of x. So this time, let's take f and insert it into the g function. So the cube root of x minus 3, and then raised to the third power plus 3. So the cube of a cube root will cancel, leaving what's inside, which is x minus 3. Negative 3 plus 3 is 0, so the final answer is x. So the answer is yes, these functions are inverses of each other. So that is it for this video. Thanks for watching and have a great day.